Hello and welcome to another video. In this video we're going to be working on maximum sum of 3 non-overlapping subarrays. And it's a pretty difficult problem, to be honest. So in this one you have an integer a, nums and integer k. Find 3 non-overlapping subarrays of length k with maximum sum and return them. Return the result as a list of indices. And then if there's multiple answers, return the smallest one. So let's just look at these examples. So in the first example, k is 2, so you want subarrays of length 2 that are non-overlapping. So if you start index 0 is here, and then 1, 2, 3 is here, and then this one. So these are all non-overlapping, and then the total here is 23. And they do tell you that you can use another array as well. You can use 0, 3, 5. Sorry, you could use this one, 2, 1. So I guess for 2, 1, yeah, so instead of 1, 2, basically they're saying you can use 2, 1, which would work instead of this one. But that would give you indices 1, 3, 5, so this is smaller. So if there's a tie, you always want to pick like the smallest one. And then in the second example, it's going to be this, and then this, and then this. I guess, yeah, they're all like, no matter what you do 2, 1 or 1, 2. So then you just pick like the 3 ones that are earliest. So I'll go over 2 solutions. Not going to go over code in too much detail for the first one, because that's the first one I came up with. It was more intuitive and it was kind of a mess. But let's start with that one. So essentially, you want to figure out how to get these 3 subarrays, but you can't do some kind of greedy thing here, because like if you just pick like what's like the biggest subarray, then you might miss something. Because like let's say I'm taking this array, but then maybe I'm missing this, or like, you know, let's say I take this, then maybe I'm missing something else. Like, so it doesn't really work because the overlapping part. If there was no overlapping requirement, then obviously it would work. Like if you can just have subarrays like this, and then that would be like a pretty easy problem. But because the non-overlapping doesn't really work, so you need to figure out a way to efficiently calculate sums of subarrays and figure out which one to take. So instead of doing that, basically, instead of like doing the instead of trying a greedy solution, there's another way you could do it. And essentially you can do a take or not take DP on an index. So like if I'm at some index, like let's just have an example of an array. Actually, I'm not even going to put in the numbers. So let's just say k is like 3 or something. So when we're on an index, we basically say like, okay, if this is the start of the subarray, do we want to take this guy? And if we take this guy, then we just take that whole array. So if we take this, we'll take these. And that's our take or not take DP. And this is a really common problem, take or not take DP. So essentially at some index, you basically say like, okay, well, I can either take the number and then go to index plus k, or not take, and then just go to index plus 1 and try all this. And this is pretty straightforward, and it would be a lot easier if you weren't asked to return these arrays, if you were asked to just return the total. Because then basically all you have to do is, you know, your take value is just the sum of the array you take, plus dp of I plus k, and then the other thing you need to keep track of is how many arrays you have left, so like arrays left. And this number is going to be small, so it's fine to have a 2D DP because you only want 3 arrays total. So this is going to be anywhere from 3 to 0, which is fine. And this would be like a medium problem, or maybe like a easier version of hard if you weren't asked to get this. If you were just asked like this question, like what's the biggest? And yeah, that's basically all there is to it. And then the base case is for that. So if number of arrays left is 0, then you just return 0 if you were asked a total. And then if not, and you're not out of bounds, then basically you can't, like, you just return like negative, or you return like infinity or something like that, right? Basically, if I'm at some index and I took, actually, if the number of, yeah, so I guess it would basically be like, if you're out of bounds and you still have to take more arrays. So this one would be like out of bounds and need more arrays. So like, let's say we choose to like not take everywhere, and then we're here and we still need 3 more. That means we weren't able to do what we needed. So we just want to return infinity, which is like a really common pattern DP. If you want a solution you want to throw out, if you're trying to get Actually, you're trying to get the minimum here, so instead of infinity, we just return like a negative infinity. Really common pattern DP. If you want to take a solution you throw out, if you're trying to get the max, just return negative infinity. If you're trying to turn the min, just return infinity. The complicated part is this array part, but it's actually not that bad because these are only length 3 at the most. So what you can simply do is instead of returning the total, you can just return the total and the array of the indices. So you can just return, like, especially if you're doing this in like Python or Go or something, you can basically return a tuple of total and array. And then in the take or not take DP, now your solution changes. So let's say we have a take and a not take. So the take, we're going to recurse to, we're going to get some value, right? So we'll have some value plus DP of I plus K, and then this will be like number of arrays minus 1. And then if our value plus this guy, the first part of this, right? So like I said, we're going to return a tuple of total and a array. So if this is bigger than this, so not take will just be dp I plus 1, and then this will be this will basically be arrays. You could also do some more logic here to ensure that you're always getting arrays of length 3, but not super necessary. So you can make sure like this has to be length 2, because if you're taking the value you're currently at, you have 2 more to go. So the thing you're returning has to be length 2. Actually, actually, sorry, I take that back. It doesn't have to be length 2. It has to be length of whatever your input into the DP is. But yeah, basically it's essentially like there's a couple problems like this where instead of returning a number, you're returning an array. And you basically just figure out, like, is this value bigger than this value? And then return either this array plus this value, which would be your array, right? So let's say this indices is like 1 and, or whatever, like 4 and 5. And then we're currently taking at index 1. We would basically just combine these two to make 1, 4, 5. And then not take is going to give us another array. So then we'd basically just return the value that's bigger plus the array associated with it. So essentially, you're going to end up having a cache of like state, right? So some state, which is going to be the index and the number of arrays. And then you're going to have a value of, this is going to be sum and the like array corresponding, right? You're going to have a cache of all these things. And then basically all you have to do here is just go through the values of your cache, find the biggest sum, get all the corresponding arrays, and just return the lexicographically smallest one, right? So you just find like what's the biggest value. Like that's a pretty easy problem. Like if I have a bunch of values like 1 and an array of like 1, 2, 3, 2 and an array of like 3, 4, 5 or whatever, 5 with some other array, and then I have 5 again with some other array. I just take every array associated with 5 and then I just sort them because it's only 3 values, doesn't matter. So you can, I don't know if like whatever language you have has an array comparison, which to see which one's smaller, but that's pretty easy, right? If I have an array of like 1, 2, 3 versus 2, 3, 4, I can just compare like the first value, then the second value, whatever, and then just figure out which one's smaller. But essentially, find the biggest value and return the lexicographically smallest array for that one. So that's solution 1. Kind of a pain to code. Second one's also kind of a pain to code and kind of a pain to come up with, to be honest. But yeah. And the other thing I forgot, actually, that's kind of important is, so when I was saying you get the sum starting at some number, right? So like, let's say this is an array of length k, and k is like some like 5, and I start here. I need to know what's like the total of this array and of 1. So that you just do prefix sums ahead of time. So on this nums, you just make a prefix sums array. And I'm going to assume you know prefix sums if you're doing this problem. If you don't, then I would start doing some prefix sums problems first, because this is like significantly harder than that. So yeah, so starting at some index, just do prefix sums to get the array you want, the sum. And that would work for DP. Okay, so the second solution, more tricky. And the second solution, basically we're going to say we can get every single middle array possible. So we need 3 arrays, right? So we're going to get every single middle array possible. And then for that corresponding middle array, we're going to figure out like what's the best left side and what's the best right side. So let's just focus on the middle array part first, which is the easiest. So essentially, like if k is 3, so we're just going to be at some index like here. And we have to have every valid index. So in order for something to be in the middle, there have to be, let's make k smaller. There has to at least fit an array on the right and the left. So if this is our array, let's say we're at this index, and we say, okay, we'll start here. This will be our middle. This is a valid middle because we can have something on the right and the left. So something like this can't be a middle because you need to have an array on the left. So essentially, we're going to try all middle arrays. So like this one, this one, this one, this one, this one, and so on. And this is just a sliding window prefix sum total, right? So essentially, you're just here. You get like, what's the total here? What's the total here? What's the total here? What's the total here? So the middle part is really easy. Middle prefix sum. But how do I calculate the left and the right? Like let's say I'm here, and this is my array. Well, how do I know what's the best in the left and the right? And I have to get this in O of 1. And you can get that by pre-computing. So essentially, you can pre-compute by saying, like, if you think about it, on the left, we want the lexicographically smallest one. So essentially, what we can do is we can just make an array of like left, and we can actually show this as an example as well. So let's actually take an example and just do a left, and then the right will be the exact same thing, but in reverse. So let me see if I have a thing here. There we go. Okay, so let's just give this some values. Let's say this is like 1 something. Okay. So this is our original array. And obviously we're going to have this stored in like prefix sums. I guess maybe we should do that. Actually, it doesn't matter. I can just compute that on the fly. Yeah, because we have k equals 2, so it's fine. This will be easier to understand. Yeah. Whoops, not that one. This one? Okay. So essentially what we're going to do is we're going to say for the left side, all right, we're going to pick some middle here. And for the left side, we need to know like where's the best length 2 array here. And we can just pre-compute here. So essentially, for the left side, we're going to say, given some end index, what's like the best array that can be anywhere before then? So like, let's say given this end index, what's the best length 2 array that's anywhere before or equal to? So like this one, or this one, or so on. And you can basically just do this in one pass. So we're going to start at the first valid index, which is here. So this is going to be the right side of it. We can't start here because it has to be length 2 or less. So we can get this with a prefix sum. So this will just be like this will just be invalid, and this will be length 6 or value 6. And then for everything else, we can just keep calculating the prefix sum. Like what's the prefix sum here? And then what's our previous value? And if this is better, then we're going to store this. So essentially, we need to store like a value in an index or something like that. So essentially, we're going to store a value, and then this is at index. This happened at index 1. So we can store like value in index or something like that. So here, the sum is 11. And so this is better. So we're going to store that. So this is 11 at index 2. And then we're going to go over here. Sum is 7. 11 was better. So we're going to keep our old sum, essentially. So here, the best is 11 at index 2. Here, the sum is smaller, so same thing, 11 at index 2. Same. These two, so same. Same. Okay, now we have a tie. And remember, we want the lexicographically smallest one, so we're gonna keep the one we had. So 11 at index 2, and now this one's bigger, so this is 13. Okay, you actually don't need to fill out the whole thing, but you can if you want to, because a lot of these are going to be invalid for the actual like full problem, but this is fine. And this is at index 9. Essentially, you're going to have this thing, and then when we pick a middle, and we're going to do the same thing for the right, so the right's going to be exact same thing, just going in reverse order. And now for the right, whenever you have a tie, you want to have the leftmost value. So essentially, you're going to go from here at this first valid location, which is here. And you're going to say like, okay, this is the total at some index, this is the total, and so on and so on. So now we know from this information, like if we pick this middle and this is our left, then we know the best value we can have here is 11. And we can get this in O of 1. And so now the full problem is basically like do a sliding window of a middle. So just, or it's not even a sliding window really, it's just pick an index for the middle that's valid, starting here, get the total for the middle. So this will be middle, plus the left, plus the right. So middle will be here. Left will always be this index, and the right will always be this index. And you can just get these in O1 now. So this is O1, this is O1, this is O1, and then you try the next middle. So that means the left and the right move, and so on, so on, so on. And you try every middle value that's valid. So like I said, there has to be at least 2 to the left and 2 to the right. So the annoying part of this problem is making sure you're not out of bounds. But now thinking about it, like, I don't even think you have to check for validity, because you're never going to get like an optimal solution will never be like, this is the middle, and then like this is the left, and there is no right or something. So I don't even think you have to check for validity. You can just like brute force maximize, and just make sure you're not like getting an error accessing index out of bounds or something. Or and probably an easier way to handle all these like out of bounds things is maybe like put a bunch of zeros on each side of the array or something like that. But that's essentially the problem. So you pre-compute the left, pre-compute the right, the best values, and then you just go through it and get a middle. So it's like a sliding window middle, which I do think is pretty ridiculous to come up with. I do think the DP one, while coding it is not so easy, I think that one's like makes a lot more sense. So yeah. So here's the code. So essentially, yeah, it was kind of a mess, and then I just like asked GPT to make it cleaner with like what I had. But essentially, you get the prefix sum. You can make a helper function to get the prefix sum, and then you basically fill in this like left best value. Same thing for the right best value, and then you try every single mid, and then for the mid you get the left and the right in O1. So this is going to be O of n and O of n. Yeah, we can run it. Yeah, I mean, I could probably optimize it a little bit more. It just took me a decent amount of time to solve this one. I don't know how this is 50% solved. Like, that seems pretty ridiculous to me. Like, I think this is reasonably difficult. So, yeah, I don't know. But in any case, yeah, that's going to be all for this one. Yeah, and this is going to be the rare Python solution. I didn't want to code this one in Go. It was too much code. So, the simpler stuff I'll code in Go in the future. So, yeah, thanks for watching.